thanks to the people still here. And yeah, today we'd like to talk about quantum batteries in the context of continuously monitored open quantum systems. And let me acknowledge also my collaborators from Unimi, Marco Genoni from UNIGE, Dario Ferraro, and my supervisor Giuliano Benenti from Insubrio. And I cannot start without mentioning, of course, Alessandro Volta, but I guess you already know a couple of things about Volta at this workshop. So, but I still find this picture quite interesting since it shows Volta demonstrating his invention to Napoleone Bonaparte and showing how important was the voltaic pile, both for technological and scientific reasons. And so the voltaic pile was made of chemical devices, and we know that the energy scaling in this case is extensive. So if we add more cells, the energy grows proportionally. Quantum battery come from a very different paradigm since electrochemical elements are replaced by quantum systems. And the energy is stored at the level of at the quantum level, and the energy can be released on demand to other quantum devices. So in a nutshell, a quantum battery is made of a quantum system that can be promoted from its ground state to a static state, and the Hamiltonian can be written in this way, where the battery can be a single system, a multipartite system, a qubit, an harmonic oscillator, and so on. The charger can be also a quantum system or a classical source, and the interaction can be switched on and off during the charging. And so why is it interesting to study quantum batteries? Both for fundamental reasons, since they allow us to study how work and energy can be stored and extracted in the quantum realm, and for technological reasons, since already some theoretical quantum advantage has been proven in charging of quantum batteries, thanks to entanglement and collective effects. The main figure of merits we need to know about quantum batteries is the ergotropy. If we have a quantum state rho, the energy of the state can be divided into two parts. The first is called ergotropy, and it is basically the energy that can be extracted unitarily. And the second part is usually associated to heat, and thereby it cannot be extracted. And already at this stage, we have some interesting phenomena. Since if we have a collection of empty batteries, of batteries in their passive state, we can still extract some work by means of global operation. And this is a quantum effect that has no classical analog, basically. And building upon this theoretical framework in the last few years, there have been some experimental realizations of quantum batteries. The first and maybe the most important is the decay quantum battery. It consists of fluorescent molecules in an optical microcavity. And in this case, we have that the power scales super extensively with the number of molecules in the cavity with this power 3 halves. And other implementations are, for example, within nuclear spin system or solid state implementations, such as quantum dots or quantum computing platforms. And what all these implementations have in common is that we have to deal with the quantum system, so we have to deal with the noise and the coherence, basically. And one way we can deal with these problems is by continuously monitoring the system. And oops, okay. So when we have a quantum system interacting with an environment, we can describe the dynamics of the system by a master equation, usually called Lindblad master equation or GKSL master equation, or unconditional dynamics. And so why monitor the system? Well, let me go back to one of the maybe most important paradoxes in at least classical information theory, that is the Maxwell demon. In this formulation, we have that this tiny being is able to monitor the position of a monatomic gas inside a box. And by putting a partition inside the box, the daemon can then put a pulley, an engine in the right half of the box, and then by let the gas isothermally expand, the daemon can extract an average work of kBT log 2. And this is seemingly violating the second principle of thermodynamics, since we are extracting work from a single heat reservoir. This is not the case, of course, since we know the Landauer principle that tell us that this cannot be done without erasing the memory of the daemon, and this erasure process has a thermodynamic cost of exactly kBT log 2. But this teaches us a nice lesson that information about the system can be converted into work, basically. And this is true also in the quantum case, maybe. So we have a daemon that can measure the environment surrounding our system, and then we can think of let's say adapt our extraction protocol to each measurement outcome in order to extract more work than before, basically. And how we can model this? Well, usually we model that in this way. We consider a stream of input modes that interact with the system and then are monitored, basically. And in this way, we can obtain a conditional dynamics described conditional state, typically called quantum trajectories, that averages to the unconditional state. And in this way, we can, as I said before, adapt our extraction protocol to each conditional state, and the energy, basically the quantity we can extract it is this demonic ergotropy, which is nothing but the averages of the ergotropy of each conditional states. And this quantity has a nice property, since it is lower bounded by the ergotropy of the unconditional state and upper bounded by the energy of the unconditional state. So we can, in principle, have an enhancement. Depending on the type of measurement we perform, we can obtain different unravelings. For example, we can perform photodetection, and this is the master equation we obtain. Or also, we can perform homodynamic detection, and we obtain another master equation, for example. And we apply this machinery to Dicke quantum batteries, as I said before. And Dicke quantum batteries consist on n non-interacting two-level quantum systems coupled to a single mode of an electromagnetic field in an optical cavity. And this is the Hamiltonian. And we also consider this kind of dissipation, so cavity photon losses, for only one Lingon operator. The protocol is simply switch on the interaction what we know is that we look at for capital, you look at the maximum energy, the maximum power, and the maximum velocity. The energy in this case scale extensively, but the power scales super extensively, as I said before. When we switch on the dissipation, basically what we see is that oops. What we see is that to zero fast, and so ergotopy here I show ergotopy and energy, the unconditional dynamics, the unconditional dynamics dissipation, and the squares and the triangles are the photo detection and detection. As you can see in this dissipation limit, you can enable ergotopy, while in the low dissipation limit, we can see that we do not recover all the variable ergotopy, but in the case of online detection, we surpass the noiseless case, which is this green curve, and this can be seen better in this picture, where I show the ergotopy, the ergotopy of the conditional state without dissipation, and we see that this ratio is greater than 1 for a very large region of the parameter space. And so we have basically an enhancement, basically measuring the system, the system with dissipation it is better than the system without dissipation. And this is, we have an explanation, since basically the correlations between the charge actually lower the amount of ergotopy, and then when the system reduces those dissipation, so in this way we can have a better extraction protocol, basically. And we, together with Marco Lamberti, and to implement this kind of system in natural cavity. Up now we have realized they have realized the cavity, and they characterize the finesse and the quality factor, but we hope soon to put some molecules in the cavity and going towards the stroke regime and see some nice results. Yes, that's it. Thank you.